Okay, I think we may be live.
Yes, we are.
Okay, great. Then as people are slowly starting, I just wanted to say hello, everyone, and welcome to this webinar, Ready to Heat, which is being organized by the European Environmental Bureau and the Cool Products campaign. And as many of you are aware now, heat pumps have become a top political priority as a key technology, not only to help decarbonize our buildings, but also to help accelerate the phase out of gas imports in light of the Russian war in Ukraine. However, there have been some questions on the potential of heat pumps in what are perceived to be more difficult sections of the building market. And this webinar by the EEB will therefore focus on the enabling technologies that can better integrate heat pumps in the grid, but also state-of-the-art technologies that can enable the quick development of heat pumps in sectors such as district heating, blocks of flats, rural areas, and old houses in the Mediterranean basins. And we have a very distinguished set of speakers who will present on different technologies for these different sectors of the building market. And we were supposed to start with a message from member of the European Parliament, Kieran Cuff. But before we listen to his message, I would like to give the floor to Heike Lebele, who is the advisor for the Greens in the European Parliament. Heike, please go ahead.
Yes, thank you very much for having me and for organizing this very important webinar. I just wanted to send apologies from Kieran that he cannot be with you online live now. He's in parallel attending a meeting of the European Commission. But yeah, he has prepared a video message for you and he hopes that you have a very constructive discussion now. Thank you.
Thanks a lot, Heike. And with that, I think we can start to see the presentation that Kieran has prepared for this debate.
Hi, I'm Kieran Cuff, Green Party member of the European Parliament for Dublin, Ireland, and also the rapporteur on the Energy Performance of Buildings Directive. But it's a real pleasure to address the EEB at the Ready to Heat symposium, because I know that heat pumps have a hugely important role to play in meeting our climate objectives. Here in the European Parliament, the big picture is the European Green Deal. We know we want to get to net zero emissions by 2050. But over the next few years, with the Fit for 55 package, we want to get to a 55% reduction in greenhouse gas emissions compared to 1990 by 2030. And even in the short term, with the awful war in Ukraine, we have a new plan, the Repower EU. And that's all about rooftop solar and heat pumps. Why heat pumps? Because they're a magical way of multiplying the electricity you have in order to heat homes and deliver real benefits for those who live there. Of course, within the EP directive I'm working on, there's lots of other things in there. We're trying to get minimum energy performance standards so that we bring all homes and all offices up to a minimum energy performance level. We're also trying to adopt a neighbourhood approach so that people work with their colleagues from down the street or down the road to work together with district heating or a common approach to improve the energy performance of their buildings. And heat pumps are, of course, part of that. We've a lot of other things in that directive. We want to be ambitious. We know what can be achieved by creating green jobs that also reduce emissions and encourage local industry, from craftsmen, men and women, from jobs for craftspeople all the way up to professional level. We know that heat pumps and other technologies can deliver. Look, with the war in Ukraine, we're saying in order to isolate Putin, we need to insulate homes. But at a more serious level, we know that improving the energy performance of European buildings, which are responsible for 40% of our energy and use up 55% of our gas. We know that we can tackle emissions, we can tackle our dependency on Russian energy, and we can create a cooler world that tackles climate change. I'm Kieran Cuff, Green Party MEP for Dublin. I'm
Okay, so unfortunately, Kieran Cuff, member of the European Parliament and rapporteur for the Energy Performance of Buildings Directive revision, could not be here, but this was his message to start the debate. And just maybe to say before we start that this webinar is being recorded, so it afterwards can be viewed also on the EEB YouTube channel. And that if there are any questions from anyone during the debate, you can post them in the Q&A or the chat function or any of the other functions on the Zoom platform. Then to start, we have a presentation by Barry Linham, who is the Managing Director of Knauf Energy Solutions, and he will focus on enabling solutions to better integrate heat pumps in the grid through demand-side control technologies. Barry, please go ahead.
Thank you very much, Femke, for introducing me, and thank you to the EEB also for inviting me today. Let me just share my screen. Hopefully everyone can see that now. Yep. Okay, thank you again for having me here today. So I'm going to talk a little bit about why energy efficiency is no longer just about saving energy. When we look at the challenge of decarbonisation, the energy system, one of the things that we notice are two sort of massive challenges which the whole discussion of heat pumps really fits into. One is the need to move away from gas and oil and to allow the renewable energy sources to expand massively to take over the existing role of carbon-based sources of energy. And that, of course, has a big issue around the fact that that also leads to a situation where you go from very stable energy sources to much more intermittent sources. But on top of that, of course, you're also having to electrify the industry sector, the transport sector, and of course, interestingly today, the housing sector. And that we see as having some major impacts in terms of how we look at the energy system and how we introduce heat pumps and we actually electrify. And when we look at the challenges of electrification of heat pumps, and we see kind of two major issues which are really important to take into account. And the first kind of major challenge is the daily constraints. Obviously today when we heat homes using gas, it really has very little impact on the grid. Whether we heat in the morning or we heat in the evening, which is typical for a normal heating cycle, even though that's when the grid is under most pressure already in terms of use, it doesn't really make much difference because we're using gas. As we go to an electrically heated world, obviously we're going to have some major challenges in terms of how we manage that sort of peak in the morning and the peak in the evening, particularly because today houses are quite dumb, right? They're not active houses. We're not easily able to shift energy use from time of day. So that's going to be for us, a really big issue is like, how are you going to manage that shifting of energy use away from peak moments to those times? But probably the bigger issue that we see and the bigger challenge that we've been looking at and we've been using our own projects to better understand and to try to get a sense of what we're facing in the future with electrification of the heating system, which we think is absolutely an absolutely essential way forward. But we have to really understand that challenge and live up to it. And what you see here is on the yellow line is kind of typical electricity demand in a Northern European country. And the blue lines are the current gas use. And the big thing that we're seeing here is that today electricity use is quite flat across the year, but gas use, of course, is massively peaking in the winter and dropping down in the summer when we need that. And this is creating a big challenge. And we wanted to really kind of use our projects and our real-time data in terms of the actual use of gas and energy to try and understand what that would actually mean for our energy system going forward. And so we did an analysis both in the UK and Germany. The figures are very, very similar for both countries. But what we see, not unexpectedly, is that as we electrify heating, we are seeing now the electricity generation going from that yellow line at the bottom, which again is quite flat, to a situation where we're going to have massive peaks for electricity in the winter, very little demand for that electricity in the summer relatively, and back up to peaking again in the winter at the end of the year. And that really creates a radically different annual demand curve than we currently see for electricity. And when we put that issue and we look at that challenge against the energy generation capacity. And just to give you a sense of what we did is we made a base presumption that in the future we'd have 1/3 wind, 1/3 solar, and 1/3 nuclear as just a starting point. Of, we're not making a view of what we think should be the energy demand or the energy production of the future, but trying to get a kind of a general perspective on what the energy mix might be in the future in a zero carbon world. And what we see is we start to compare the demand curves, these new winter demand curves and lower summer demands against the intermittent production of electricity. Because of course, as we move to wind and solar, one of the things that we're going to see is, particularly in Northern Europe, much lower solar generation in the winter, but also periods of very low wind generation where you're going to have very high demand meeting very, very low production. And we call it the peak trough challenge. The challenge between the peak demand, which is coming in the winter, and the generation troughs, which will probably happen most years in terms of energy generation. And when we look at what that means in terms of the full capacity of the energy system, we start realizing that actually, whilst demand for electricity probably only doubles, the need for generation capacity goes up. In this case, when we're looking at the UK environment, but also very similar numbers for Germany, we're looking almost 5 times more generation capacity that needs to be built to be able to make sure that when we have this peak trough moment, we have enough generation capacity. The good news, though, and this is why we talk about the reason that energy efficiency isn't just about energy saving anymore, is because as we look at the impact of energy efficiency measures, we notice that we can massively reduce that peak generation need. In fact, for every kilowatt we reduce in terms of energy efficiency in the building stock, we see a 4.7 times, or in Germany, a 5.2 times reduction in the necessary to oversize that grid. So we're not also talking about not doing more renewables. We know that there's going to be an absolute need to massively increase the renewable generation capability. What we're saying is that if you're not careful as we electrify the building stock, we're going to have a massive oversizing of grid capacity. Because one of the things we also note is that in this kind of peak trough world, you end up also in a summer situation where you have massive overgeneration capacity, which is lying idle because the need for that heat just isn't there. And so it really means that in the future, energy efficiency isn't really about the saving the energy in your home or my home. It really becomes about how do we make sure that we have a generation capacity environment which makes sense. And for me, this very fundamentally changes the debate about energy efficiency, because it no longer is about the money that we save as individuals. It's about the reduction in the generation costs of our entire energy system. And therefore, we have to rethink also how we see the support mechanisms that go around this challenge. And our perspective at Canal Energy is that when you're talking about removing grid capacity, so in this image, in the bathtub image, the tap, if we're talking about reducing the amount of generation capacity, so we're currently presuming in the OECD countries a 1.6 trillion a year investment in the taps and only a 211 investment in energy efficiency. Tells you whether energy efficiency first principles actually in the real world isn't really there, right? So we're far from that principle. But what you're saying here is that in the future, we're going to have to transfer more and more of that funding away from the tap towards the efficiency, because that's where we're going to get the biggest bang for our buck. But no government is going to turn off or not build new power generation for fictive energy savings. We're going to have to move to a world where we can absolutely guarantee that energy efficiency capacity that we've created, that virtual power plants that we're building, are delivering real capacity reductions. And we're going to have to understand the energy efficiency of a house in real time, really understand the thermal performance, to offer management services, to go back to that first slide, which is how do we solve the daily peaks and the daily demands? And that's what we think is absolutely essential. And unfortunately, today, the energy performance certificates are not fit for purpose for this more dynamic world that we're going into. So what you're seeing on this graphic on the bottom is the energy performance certificates that came out of, for house 1, house 2, and house 3, came out of a project that we're working on right now where we renovated 165 social houses. And we just took some of the typical kinds of energy performance certificates that we were getting from those projects. And As you can see, as an example, house 1, the energy performance certificates were assuming a 687 kilowatts per square meter. So a house that was nowhere near ready for a heat pump. When we used our monitoring capabilities to understand real-time performance of buildings, what we saw that house 1 had a real energy demand of 143 pre-retrofit. And alternatively, house 4, which was from a project that we weren't involved in, but we were asked to come and look at a house that was underperforming, we had an energy performance certificate that was saying the house was 20 kilowatts per square meter, and its real energy demand was 220 kilowatts per square meter. So a massive, massive under and a massive, massive over assumptions, meaning that if we're really going to be right-sizing heat pumps and right-sizing the introduction of energy heat pumps and managing those houses in real time, the current structures we have, unfortunately, are not going to provide the data from what we see in terms of the kinds of real-time data you're going to need to have to be able to manage that house correctly, but also to make sure you right-size those heat pumps and we get the right type of solutions in. So that's kind of where we come in as a company. We've developed what we call the negawatt hour capability. What that means is that we can now, using sensor technology and algorithms, we can understand the real performance of a house in real time to a very, very high level of accuracy. It works by bringing a group of sensors into the house, taking some basic sensor data in terms of also things like indoor air quality. So we also understand the comfort also issues with retrofit, and allows us with that graph on the right to be able to meter in real time exactly how much energy savings and how much capacity savings in the future are being delivered by retrofits. And also to kind of establish trust amongst government and amongst homeowners that this is really, really actually delivering the energy efficiency. But I'm not really here to talk about our technology, but that's what we kind of brought to the market. And I'm happy to talk to anyone afterwards or other times to explain how that works. But importantly, what it means is that as we start to roll out heat pumps and we start to electrify our systems, as we start to realize that we can't oversize our capacity generation, otherwise we're going to really struggle with this massive decarbonization of our system, we can start completely rethinking the way we support energy efficiency and we support the rollout of heat pumps. And what we can do is we can think about actually pay for performance approaches where, as we can produce megawatts, we can also now pay for that capacity generation. And one of the things that we think is absolutely essential for the next phase of the rollout of energy efficiency, but also electrification, is developing capacity payment mechanisms for energy efficiency. And one of the things that we're seeing as absolutely missing, and I think we think is a vital policy change that needs to be brought to bear, is capacity payments on the energy efficiency side, not just on the production side. And if we can develop those kinds of pay for performance approaches, which allow that capacity that's being demonstrably taken out of the system to be rewarded by the system, we can accelerate energy efficiency. We can accelerate the heat pumps going into the system, make sure the heat pumps are properly sized for those houses, and make sure that we can actually get to where we're trying to get to as a society, where we get a large amount of renewable power, but we also get a heating system which matches that renewable in a way that doesn't mean we have to massively oversize. And just in terms of some of the numbers, so because we do the retrofit, so when we do energy efficiency, we are a full one-stop shop. We do the retrofits from design through delivery, plus we know the real savings. We know from our first sort of data from projects is that the energy efficiency savings are cost about 1/3 the cost to do the energy efficiency than it does the generation capacity in this kind of model. And so it seems to make a lot of sense to move in this way. And it means really that, heat pumps and energy efficiency actually work together with that renewable generation to make sure we have an energy system that works for everyone and make sure that we can drive down costs for people as we move to this new environment. So that's what we're looking at and how we're trying to help the rollout of heat pumps and making sure the generation capacity is correct. Thank you, Femke.
Thanks a lot, Barry, for this presentation and interesting overview of your technology as well to help with this and to help make sure that we don't oversize also the electricity kit and make sure heat pumps can be integrated through efficiency solutions, which I guess is very important, especially as the number of heat pumps go up. Then we have now the next presentation by Claudio Carano, who is the project marketing manager at Clifford, and he will focus on solutions for the Mediterranean area, but also beyond. and in particular solutions that could work for unheated dwellings, but also rural homes. And maybe already just to indicate that Claudio can only be with us shortly after his presentation still. So if there are any questions on his presentations or in general about the technology or anything else, please do post them already in the chat in the Q&A so he can still answer them. Claudio, please go ahead.
Thank you very much. So let's share the screen and let's start. Thank you very much. I hope you can see my screen now. You can just, so now it should work. Can you just confirm you can see the screen? Thank you very much. Thank you very much for this introduction. I'm very happy to be with you from Italy, near Venice. And as already mentioned, I would like to share with you some live experience from the Mediterranean areas. And what can I say? The heat pump technology is a really perfect matching with this kind of climate and let's say application. First of all, because the heat pump is not only heating, as very often is, let's say, thought in northern areas, but it's an important resource, especially on cooling. So in summer cooling, this is a dominating function in summertime. And this is valid, this can be useful in a residential, commercial, and industrial application, not only in residential. But let's focus now on residential buildings. This is the topic we are focusing now. Let's start from the needs. I would say everybody's experience about space heating and cooling, domestic hot water, and I would say more and more the indoor air quality control. How heat pump can match with this kind of needs? They can really fit providing high primary efficiency. You know, the current European regulation is able now to measure the primary efficiency and compare different technologies for heating, like, I don't know, fuel heating, electric heat pump heating, hybrid heating, and so on. One of the big benefits is having no local CO2 emission and resulting in a optimal TEWI. TEWI is a very technical parameter, a KPI. It means total equivalent warming impact. And basically this is composed by two factors. One is the direct, for example, relating the direct greenhouse global warming. This is, for example, related to the refrigerants, the risk of leaking from refrigerants. And the other one is the indirect global warming. This is the second factor, the indirect global warming, is much, much bigger, something like 90% of the total. And this is related to the energy consumption. So it is very strongly connected to the energy efficiency all over the life cycle of the system. There are different kinds of heat pump technologies and, let's say, layouts solution, especially in the Mediterranean area on residential application. One of the most popular has water on the load side. It means, for example, as we can see on the high part of the screen on the left side, having a central heat pump, then water lines providing water, for example, on radiant panels or fan coils. This is a quiet system. This is suitable in renovation as well. Or as we can see on the lower part of the screen, this system can be integrated with a ventilation heat pump as well, central energy assistant. And as we have seen from the previous speaker, we can also integrate this system with energy storage system, for example, in order to benefit from the electricity produced all over the day. This system has a top efficiency, and this is able to provide indoor air quality in addition to the previous one, and smart control to minimize the energy impact. Or, and this is very, very popular in the southern Europe, so in the Mediterranean area. On the load side, the system, the heat pump can provide the air as a heating and cooling, let's say, medium. There are different solutions. For example, sorry, just, okay. For example, there are some units, as we can see top right on the screen. We're talking about single package having all function inbuilt, so the ventilation, the cooling capacity, heating capacity, domestic hot water, and they are especially, let's say, suitable for new buildings. While another very popular solution is based on very popular split or multi-split units and additional specialized unit to provide, always with the heat pump technologies, providing domestic hot water. This is very fast as far as the installation is concerned, and this is also able to provide a fast response when switched on. And that's why probably is one of the most popular all over Southern Europe. We will focus on this system. Let's see together which kind of components are this system based on. So let's say the main heating and cooling to cool down or heat up the space are typically multi-split units. They are air-to-air heat pumps, latest technologies, full inverter, very high seasonal efficiency, and a large variety of indoor units to fit with different, let's say, indoor design. And probably the less known, the less popular, but very popular in numbers, to be honest, heat pump is the domestic hot water heat pump. It looks like we can see on the left, on the right part of the screen. It is basically a tower where the heat pump is located on the upper side of the unit, together with, let's say, controls. And the lower part is a big, let's say, usually 200 to 300 liters hot water tank in order to provide fast domestic hot water for shower or bath, for example. These kind of solutions are, to be honest, already very popular. The growth in the European market, I'm talking about new heat pumps sold year on year, is really impressive. We can see here the progression from early 90s up to 21, including all the, let's say, the key European markets. If we focus on the sanitary hot water, so the tower we have seen a few seconds ago, combined with the air-to-air, we're talking about less than 1 million pieces. This is the total market tracked in 21. This number is more or less close to 50% of the total 2 million heat pumps provided in 21 in Europe. But the most, let's say, exciting and challenging projection is what will happen in the next, let's say, 10 years. This is the expectation, let's say, the European ambition. These charts are from EHPA relation meeting with the European commissioners, Kadri Simpson. And we can see the progression is very, very impressive, leading to something like 12 million in 2030, 12 million pieces, where more or less half of them are expected to be exactly the system we are talking about for South Mediterranean area. So split and multi-split units plus sanitary hot water packages. Just to share some real experience and to become a little bit more familiar. Probably everybody is very well familiar with split and multi-split heat pumps, while the domestic hot water heat pump may be something a little bit unknown or strange, but we will become more and more familiar with it. As far as the size is concerned, it is more or less like a fridge. So it's a tower, a vertical tower. It is more, from the sound point of view, is more quiet than a split unit and can be usually located in the box, in the laundry, in the kitchen and so on, and can also benefit from thermodynamic solar energy from thermal panels, for example, if and where the house is equipped with this kind of technology. It is a very fast system. Usually it is known as a fast system. And the popular application can be the rural homes, for example. We should always remind that according to the European Commission figures, over 30% of European people lives in rural areas, or vacation homes. Over 500 million nights were spent in vacation homes in 29. So we're talking about really a massive application area, or passive houses and social housing as well. Let's say the kind of response for this kind of system is very similar in all these kind of application. This application can be off-gas grid. The solution is scalable, so allows the users to increase capacity time by time, especially is very fast response, so is able to cool down or heat up in a very short time, just because the medium, let's say the heating and cooling effect is immediately reversed on the indoor air. Very important in the southern Mediterranean area, in the southern European area. All these systems are able to provide cooling as well, not only heating, in an efficient way. And this is, I would say, a must nowadays. All these systems are IoT connected, so they can be immediately driven by apps, individual apps, or can be connected to a more sophisticated demand response system from home to the grid. This is, to be honest, I'm coming from the industry, and this is an opportunity also on the occupation point of view. Currently, over 170 factories are involved are directly involved in the heat pump evolution all over Europe. All technologies, despite it is a water or air technology, all technologies are growing, so there is no major shift in demand, and this growth is the size, the magnitude is a double-digit growth year on year. I would like just to share our own experience. We are based in Italy, and we are part of a global group based in Asia. And to be honest, we faced a real example of reverse delocation from Asia to Europe, to Italy, to be more specific, in 2017, when the domestic hot water technology was moved from Asia to Europe, to Italy, in a very few months. And at that time, the capacity, so we set up production lines able to produce in a very short time 12,000 pieces per year per each work shift. So this resulted in a very good opportunity also from the people, from the, let's say, social and the community point of view. This is just an example. We are very well involved and committed in the next developments, not only our company, in a so fast growing market. New sustainable factories are, let's say, the result of large investments. And this, of course, leads to a, let's say, amplified occupation jump, not only on the production, but on the whole supply chain. That's all from me. I would like to thank you for your time. This was just a short sharing of our own experience. If you have any question, I'm fully available. Thank you very much.
Thanks a lot, Claudio, for your presentation. And if I may follow up with just a quick question, I was wondering if you can say a bit more about what were the reasons for relocating from Asia to Italy for the hot water heat pump production?
That's a very good question. Thank you very much. There are several topics. So the easiest answer is to be closer to customers. And to be honest, nowadays it means despite, let's say, the cost of the labor, the flexibility of having a local, let's say, European production is a key driver. All the issues on the transportation we have been facing in the last years, let's say, accelerated very much this trend. And to be honest, I would say also the quality of our factories, of our workers are well recognized, not only in Europe, but also abroad, let's say out of Europe, especially in this combination of, let's say, what we call DX technology. So the technology with the refrigerants and let's say the combination with the water technology, where Europeans are really among the leaders worldwide.
Okay.
I hope I hope the feedback was complete.
Yes, I think it's very clear. Thanks a lot for that answer. And thanks a lot for your presentation. And just again, I realize you have to leave. If there are any follow-up questions on your presentation, either by any of the participants or panelists, let me know and we can maybe ask them before you leave. But if not, I will move on to the next presentation by giving the floor to difficult to pronounce for me, Morten Dedding, Director for Heat Pump Application at Johnson Controls, and he will tell us a little bit more about district heating and heat pumps. Did I pronounce that right?
That was a really good first try, I'll tell you. So heads up, really cool. I'll see if I can share my screen. Ta-da! Are you able to see it now?
Yes.
Super. Thank you for letting me have a go at and for inviting me. It's another kind of heat pumps that we do. I represent Johnson Controls, and we do large heat pumps. That's our game. And many of the heat pumps here, we are talking hundreds of kilowatts or megawatts. And our game is utilizing either renewable energy or waste energy, and then putting them into a district heating system or a large central heating system. I've been in this game for many years. First as a consultant, later as a product manager and a business developer. In Johnson Controls in Europe, the cluster that I work in, we are represented in most of the countries. And we have actually put a lot of megawatts of heat pumps up in the last year. I know compared to residential heat pumps, the market is maybe not that big, but it's still a significant business. And the numbers we saw on the previous, we can relate to that in industrial. That's not so much intelligence, but the market is growing roughly the same way. I wrote in the first one that heat pumps is striving for performance, but it's always a balance. It's a balance towards utility companies demanding robustness and durability and long service intervals. On the other hand, they also like performance. So right now there's a shakeout of technologies. There are multiple refrigerants in place. I would say for these kind of large installations, it's more or less always low GWP refrigerants on centrifugals, or it's natural refrigerants on reciprocating and screw compressor design. But let's see some examples. Let's see some examples. The first one here is a dear customer, a dear partner, and sometimes also a competitor. But this is actually a good example of how you utilize energy that are normally wasted so in production of plastic molding. you need to cool the molds or the patterns you have. And that normally is done by an adiabatic cooling tower. So you simply evaporate water to get rid of the waste heat. Instead here, in a large factory, in a large system, you can utilize the heat almost all year around. So these heat pumps here are fired up by the adiabatic towers, waste heat, and then provide the facility with heat, 2 megawatts roughly in this place, COP of 4, payback of a system like this, less than 5 years. It's a complete no-brainer. On top of this, it actually saves the customer 1,500 tons of CO2 and also 35 tons of water daily had they not used the heat pump. So on top of just being a good business case, it actually also adds to the sustainability image by saving water and reducing carbon footprint. But again, here, waste heat normally just put out in the open. So this was waste heat. I have another example here. It's heat and cool. You have a facility that demands cooling 13 degree to 7, and a heating plant 50 to 60. But as we also heard on other of these, is that the balancing. So in this case, a brilliant idea. This is from the Czech Republic. This is actually a customer who has a cooling plant where he uses cooling in his production. On the other hand, he has a heating plant where he uses natural gas. And then he has a large 1,300 cubic meter reservoir for sprinkling water. In case of fire and there's a malfunction in the water supply, he has a tank ready. So what we simply do is, during the day, we run the chillers. That the waste heat from the chillers is put into the buffer vessel or the sprinkler reservoir. And then, as we demand the heat, we simply empty the buffer vessel. So here, actually, by a fairly simple interaction and combining a vessel we actually already had for some other use, we actually made a pretty cool system that can balance. And this is an example also of what we see in district heating, is that utilizing waste heat when it's available, storing it, and reuse it. I have another example, and it's actually showing you exactly the same. This is a data center. This is a large data center. This is 20 megawatts of cooling capacity, producing 27 megawatts of waste heat. And in this case, the waste heat is removed from the data center, put into a district heating network of a city with over 100,000 people. And this actually provides heat for 7,000 homes, roughly 20,000 people, or 1/5 of who actually lives in a city. So a data center from Microsoft, Google, Facebook, whatever, placed next to a city with a district heating network, one of these centers, and here is actually more than one center, but just one center is actually 7,000 homes or 20,000 people. So placing large data centers next to urbanized areas is something we will see in the future. This was short-term use of waste heat. I also have a system here with a long-term use of waste heat. In the bottom right of the Mac computer here, you can see an illustration or a picture. This is in fact a solar thermal park. On the left picture, you can see an energy uptake system. So this is just a 6 megawatt air to water system, but it's actually also here in the next to the ambient air exchanges is a pit, as 80,000 cubic meter water storage. So during the summer, when it's hot and you don't have a demand for heating in the city, you simply heat up this old gravel pit, 78,000 cubic meters of water. And then during the winter, you can actually take up this water and you can fire up the heat pump. You can also have situations where it's actually more applicable to use the ambient air as a source, and then you can save the water for a really cold day. But this actually means in this case that the city here provides roughly 40% from the solar thermal directly, and 57% of the heat in this city either comes from air to water or water to water stored during the summer, used during the winter. And the system here, the thermal storage system, has an efficiency of 78%, which I find extremely a fantastic efficiency. But this ends up being a city that has a 97–98% carbon neutral heating supply for a full city. It's actually only during days when it's more than -15, they have to use their old natural gas boiler as a backup. Yeah, if I can do, I have one more. European Heat Pump Association issue every year a small contest where you can win an award. And last year, Johnson Controls entered one of our dear customers. It's not the company who wins, it's actually the customer. This is, you can go and see it on the homepage of EHPA if you want, but it's actually an office building, and the office surface is covered in 3,000 square meters of solar panel, PV, photovoltaic. The whole building is solid. It's made with a lot of concrete. So during the night, on the hot days, we use the seawater to cool the structure of the building, minimizing the cooling needs during the day. Also during the winter, we heat up the building and then store energy during the night. So a very stable system, running very low temperature. And in the basement is a single heat pump from Johnson Controls. This building from the photovoltaic system actually produces 500,000 kilowatt hours per year. Half of that is used inside the building for computers and lighting and coffee machines and whatever. And the rest is used for heating purposes. Apart from 5%, this building actually contributes 5% of the energy into to the grid. So it's actually a net positive energy building. And it's located in Trondheim in Norway, close to the northern hemisphere. So if you can do that in Norway, you can do that everywhere. So there was just a few examples of how large heat pumps can interact in these future sector couplings that we will see, how we, from industrial point of view, see options in how to utilize waste heat from industry, from whatever, and reuse that in a large heating grid. This is not a competition to residential heat pumps or commercial heat pumps. This is a supplement where it makes sense. So this is our contribution. Yeah. A couple of pictures of a system from Paris, an 11 megawatt heat pump, 500 tons, 8,000 kilos of refrigerant charge, HFO, low GWP, 1, 2, 3, 4, ZE, 4 megawatt motor. So heat pumps can also be large. Yeah, please, any questions?
Thanks a lot, Morten, for this presentation. You can maybe stop sharing if you like. It's very interesting to also see the large-scale applications for heat pumps and how it can be combined with other sectors. I would just like to go back to Claudio, because in the meanwhile, there has been a question in the chat, first of all, around the use of F-gases in heat pumps. So F-gases are very polluting greenhouse gases that are used as a refrigerant. And second of all, as Islene is from Portugal, she had a question about what about apartments where there can be difficulties for having heat pumps due to a lack of space or split incentives for it, for example. Claudio, the floor is yours.
Sure, thanks a lot. Both questions are really good questions, and also, let's say, tough questions, I would say. On the refrigerant point of view, the migration from very, let's say, polluting, technically the name is very high GWP, so global warming potential. This is how the pollution can be measured. The transition from very high GWP refrigerants to mid and low GWP refrigerants is really in progress. I would say most of the, let's say, most of the equipment, most of the technologies have already turned from high GWP to mid GWP, and I guess everybody knows about the new F-gas regulation draft. This is pushing more and more on the naturals. So this is welcome from the industry as well, and this is, of course, the right way. Just the time should be suitable to turn, let's say, technology in that direction. But this is something really happening. So I would say the pollution of refrigerants is probably, I would say, already in the pipeline to be solved. And on top of it, I would like to remember, at least on air conditioners and heat pumps, the direct effect is usually around 10 to 15% of the total global warming risk, I would say. So the rest is let's say, coming from the efficiency. Higher efficiency means lower indirect emission, and vice versa, of course. So I guess all the industry members are pushing not only on refrigerants, but as we have seen with Morten, also on a big application, everybody is pushing on both refrigerant compatibility and higher possible efficiency in order to get, as a result, the best combination as far as the global warming effect is concerned. Moving on the second question, we are really, the question is about the constraints sometimes we are facing in order to install a heat pump in our house. The variety of application is, I would say, huge. The question was talking about, for example, we are not the owners and the landlord doesn't want us to install a heat pump. I guess we are really in a cultural transient, not only technological transient. I would say the heat pump revolution is has just started. More and more, I can see three effects, three, let's say, topics that needs to become more and more popular. Is a global awareness, also from the landlords, on this shift and the reason of this shift. Also, the let's say how can I say it? Using heat pumps often means also redesigning homes. I would say all the new buildings, most of the new buildings are already natively designed on heat pumps. So the where to locate the heat pumps and how to operate heat pumps is not an issue. Of course, on older buildings, this can be a topic, and that's why the variety of solution is increasing more and more. We have just seen a couple of examples with water-based systems or air-based systems. Let's say in most situations, the solution is affordable. And I would say the third topic is related to the global policy. I would say we know, for example, in UK, the fuel heaters, the boilers have been banned on new build and so on. So the more, let's say, also the regulation and let's say the laws will push on heat pumps, the more all the operators on the supply chain, including the landlords, will be aware on this technology and will, let's say, step by step, move this transient to this to its end in order to have really heat pump as a standard heating and cooling equipment and not only gas boilers. Morten?
Yeah, just a comment around the refrigerants. For the large heat pumps, due to efficiency, it's traditional to use natural refrigerants or low GWP refrigerants. That being said, and as much as I come from a background, we also have to be realistic, and that's why I was really like to see that somebody brought up the total environmental impact and the TV factor, because if we are to fulfill the market needs in the next coming years with the ramp up of heat pumps, of course, we need to phase down and have the impact of the F-gas. But if you look at it from a holistic point of view, a heat pump with a refrigerant with a, let's say, 500 GWP, can in its lifetime actually saves much more carbon than it would release if it leaked. So we should, I know we would like the F-gas to get down. We would also like the penetration of heat pumps to go up. I think we need a holistic view on the F-gas. The phase down, no, I don't know how long it should be, but the TV is one way of looking at it. And again, if we are to serve the market with the units in front of us, we also need to be holistic about, hadn't we had a problem with global warming, we could have phased down much, and with scarceness of fossil, we could have phased down faster if the demand would have been less. So I'm not fully aligned here, but yeah.
Okay. Thanks a lot. I think this may also be a topic maybe for the discussion later, but thanks to you both, and thanks also Claudio for the answer. I think based on what I saw from Islene, she was very thankful, so I think that answered her question. Then I would like to move on to the next presentation by Helen Karlström, who is Senior Manager for Growth and Sales, and in particular responsible for city corridor solutions at E.ON. And she will talk a little bit more about low temperature district heating and heat pumps. Helen, please go ahead.
Thanks. So then I will share my presentation. I hope this will work. Can you see the screen?
Not yet.
Okay, soon.
Yes.
Now.
Yeah.
And So I will talk about, I do come from a business that works with district heating and district cooling and a lot of electricity grid. So E.ON is a large energy company. Myself, I come from the more large-scale generation distribution of district heating and district cooling. And first, I've been told not to be too technical here. So I start with one example of what we're doing with this technology we have been developing. So this is a system in Lund. It's in the southern part of Sweden, where we've been connecting several buildings, a combination between retrofit buildings and new built buildings, and it's both commercial buildings and residential buildings.
Helen, just to say that we're still on the first slide.
Okay, so you cannot see this second slide.
No.
Okay, I will try to leave that presentation mode. It looks a little bit strange in my browser as well. Can you see now?
Yes. Yes, we see it.
Do you see the second one?
Yes.
Hopefully it will work now. Looks, I use Teams all the time when sharing, so. Otherwise, I will only go off the presentation mode. But anyway, so what we've been doing is that we have been combining in a two-pipe system, a cooling and heating grid in one. And I will try to explain how we are doing this. So what we're essentially doing is that we are sharing both heating and cooling in between buildings. So do you see this slide? Did it shift?
Yes, it did.
Yes.
Okay, good, thanks. So for now, it's about, come on, such a technical hassle. So we have about 15 commercial and residential buildings connecting, and this area, this is not working.
So you can click on pause. There's a pause button on the top of the slide, maybe.
Okay.
Du skal bruge visningsindstillingerne, som er i menuen midten øverst.
Okay, is it paused now?
It is.
Okay. But now on the other hand, on the wrong slide. It looks super strange. Anyway, so what we have been doing is,
if you go in the upper visningsindstillinger, in the upper of your screen, click on the pilen, der går nedad.
Okay. Okay, I stop sharing and go back again, I think. Because now it's sharing in so many places. So okay, I give it a new try.
If you can go back maybe to the previous slide you were.
It's moving by itself.
Yeah.
See if this works.
We only see the challenger slides. Could I always otherwise ask you to perhaps to share the slides for Helen?
Yeah, or sorry, it's Claudio again, as Morten said in a very more professional pronunciation that I could do. If you go on the top menu, second bottom from left, these I cannot pronounce it. And there is a screen with a wheel, with a, if you can go.
It's the one that said Visnings instead.
Exactly.
Yeah.
Morten told it perfectly. Sorry, Morten.
Press the drop down.
Yeah.
The arrow down. And then you have an option to flip your presentation screen and your back screen.
No, it doesn't. It doesn't look like normal, you see.
Elena, can share your presentation. If you stop sharing the screen, I will do it for you.
Sharing the screen. Yeah, sorry for that. I've been sharing so many times on this, but it's some other mode on this. Okay, thanks. So if we resume, this is about sharing energy between the buildings, and I will come back to how we are doing this in practice. And in the overall, by connecting these buildings on this site, we have been reducing the energy demand of the area as such by about 65% compared to if we were adding heating in one pipe and cooling in the other pipe. So this is it's quite a big area. It's about 120,000 square meters altogether and growing, and it's a very mixed demand, both pharmaceutical companies, research companies, but also normal traditional residential companies with the demand of heating and domestic hot water. So if you move to the next one. So what the challenges we face, if you step on, if you continue, and what we see are driving this development we're working on is that we see more and more people move to the cities, and we are going more and more electric because we want to get rid of combustion. It does not only have to do with CO2, it also have to do with the NOx footprint. So we cannot burn things as much to create energy for also health reasons. Okay, now you also struggle with this. So if you move back again. We do see that also we have an electrification of the transport sector. And for now, for new establishments, the grid connection required by the e-charging or charging by electric vehicles is actually the highest capacity demand of the developments. We do also see that more and more buildings are requiring cooling, also residential, and not only in the very southern part of Europe. And what we are also struggling with, that our energy systems produce high volume of waste heat. So for instance, we have as much cooling demand in London as we have heating demand. Not absolutely at the same time, but a big, massive overlap. So if we take the next one. So today we are quite good in recovering the waste energy, the waste heat that has a higher temperature. And that is in areas, especially where we have district heating. So like in Sweden, Denmark, Germany, some parts of Europe, we have large district heating grids. Then we recover high temperature waste heat. But all the other waste heat with the lower temperature, we cannot recover with the technology we have today. And this is what we're doing in this system. So when walking through a city, you do know, and you do notice that there's a lot of heat being expelled to the air. At the same time, we fuel and heat our buildings with gas. And this at the same time. If you take the next one. So what we're doing, this is a very fancy way on how to explain what we're solving. Of course, it's not that straightforward. But what we're really trying to do is that we try to combine these different thermal needs before adding new energy to the system or remove energy from the system. And it's an electric system mainly, but it can be balanced with other means. We try to both minimize the CO2 emissions, but and be flexible with accordance to the actual electricity consumption. But we very much try to remove combustion. We do not think that's going to work in the long run. We take the next one. And now we are going into a slightly more technical presentation on how we think this is doable. So if you click here, I think this might be the problem with my presentation is too animated. So before we had in older buildings, the energy consumption is rather high, higher in some countries than others, but this is going down in all countries. So for older buildings, we have higher energy consumption, and for new buildings, we have quite a low energy consumption. That also means that if we have a low energy consumption, the losses we have in traditional district heating is too big to deliver that small amount of energy, relatively small amount of energy. The proportion will be wrong with high temperature district heating. Even if the losses are not massive, but they might be 5–10%. That means that we have an awful lot of pipes in the ground delivering smaller energy volumes. And that's not a very sustainable way to be doing things. And then we also need to have combustion to produce that high temperatures. But at the same time, if you click again, in new buildings, the temperature that is demanded in the building for comfort heating is much, much lower. This means that we do not need to have 90 degrees or 80 degrees anymore for new buildings and buildings that are renovated. This is a little bit of a hassle for us, I think, working with heat pump system, is that in some countries in Europe, it's not really regulated. It's regulated how much energy the building consumes, but it's not really decided what temperature demand they have. So of course, we do not need to use 60 degrees when it's 15 degrees outside. We want to have outdoor compensated energy curves. So, but really, if you have a big district heating system, and if one customer do need to have 90 degrees, that means that you need to put out 95 degrees from your energy plant. Because you always, it's a passive system. So you need to put out temperature in the system that the customer with the highest demand do require. And I think it's quite clear, that's a waste. That's a centralized system. It will be waste because most of the customer will not demand that kind of temperature. So if you take the next one. So, and this is what the development of district heating and also looking into the future district cooling system is about. It's about lowering temperature, because lowering temperature means also reducing the losses. So, and also when building new systems, you cannot build a district heating system and a district cooling system in parallel. That means you have to put 4 pipes in the ground. That costs a lot of money, and it's also consumes a lot of space. So if you take the next one, so this is what we call the 5th generation. And now I will try to explain how this works. We do put heat pumps and cooling machines in the buildings. And as earlier said, a heat pump is the same thing as a cooling machine, pretty much, but installed in another way. So what we do is that we put a machine that is acting as both a heat pump and a cooling machine in the building. And if the building is in need of heating, it takes from the warm line. The warm line might be about between 10 and 35 degrees, depending on what's available. This temperature is boosted to the temperature that specific building do need. At the same time, cooled water, then the water will be colder on the other side of the heat pump, is going back to the cold line. That cold line might be, depending on the time of the year, we can control and steer that output, maybe between 5 and 15 degrees, let's say. That cold water is going back to a customer that do need to have cooling. So their cooling machine will work very efficiently, and they will use the energy to be putting back their excess heat, because cooling something is really removing energy. That energy is going back to the warm line. If the customer have both need of heating and cooling, for instance, both cooling and producing domestic hot water the same day, they will balance this within the building, and the excess will be put back into the grid. The pumping of the system is distributed. So in each and every building sits frequency control pumps. And this means that this kind of grid can go 2 ways. So there is not a supply and return as in a traditional grid. So it's a bidirectional system. And each and every of these buildings are connected to a control platform, because we really try to use electricity when it's needed. So heating and cooling is quite slow. So we know when a lot of cars, for instance, needs to be charged, we cannot operate the heat pumps at the same time. Then we will have a problem with our capacity. So we try to boost the system and be prepared. And this is what we are teaching the system and how to behave. This system will not be in balance at all time. Most of the time it will not be in balance. Then we need to put in additional energy into the system or remove energy from the system, either of, depending on the time of the year and the profile of the consumers. But this is a way to build infrastructure in cities to reduce the overall electricity demand, and also to produce deliver heating and cooling without expelling excess energy onto to the roofs of these buildings. You take the next one. So this is a system that we do not operate this with a traditional control room as we normally do in E.ON with energy plants and so on. This is more an automated system. Of course, there are alarm functions and so on, but this is a system that teaches a little bit itself on how to operate. There is not, I would say, being used to combustion. It's not a dangerous. There's nothing dangerous in the system. It's not boiling water, no fires, nothing. So it's a quite system that is possible to operate in this kind of manner. So we have it, of course, connected and online and supervise these systems, but it's another way to operate district systems compared to traditional system with a gas CHP, for instance. We use standard components. For instance, we could have used Johnson Controls heat pumps here. We do not produce any of these heat pumps or anything. We want to use traditional water piping, not complex steel piping as we normally do. We want to be able to put this into the ground together with, for instance, the local water companies. And we really would like to emphasize this is infrastructure that new customer could connect to, because it's a modular system and scalable after time. The next one. So these again are the main components. Here, to make it more clear, we've been putting it as a heat pump and a cooling machine in the building, but it's really the same machine. So instead of heat exchangers in the buildings, there are active components with proper substations containing of heat pumps that then are connected to the system that we then call Ectocloud, and is the control system. We need some kind of to keep the pressure and have a 0 point in the system. We have a balancing tank, mainly, normal water tank, and then we need to balance this system. But if, for instance, a customer do have excess energy, for instance, in an office, a warm day like today, that excess energy is going into this tank, and at night when the residential customers come home and they want to do their dishes and take a shower, they empty this tank with energy. And the overall efficiency of such a system will of course be very high. We can take the next one. So to manage this, we do connect all these assets, and we do control it with regards to the energy market and also the weather forecasts. So sorry for the messy presentation in the beginning, and happy to answer questions on this if any.
Thanks a lot for your presentation, Helen. And I think that sort of outlines also the importance of a district approach to renovation, which I think is also an integral part of the report by Kieran Cuff on the EPBD, the Energy Performance of Buildings Directive. Okay, then we move to the last presentation of today before having some time left for questions and answers, which will be by Ferdinando Pozzani, who is the co-founder and CEO of Tion. And this presentation will be focused on centralized heating for blocks of flats with high temperature heat pumps, for example. Ferdinando, go ahead.
Thank you. I hope you can see my screen.
Yes.
Fine. Who's Theon? We are a relatively new company. We're established in 2015, following a period of research, of applied research, that brought to the creation of a family of products of heat pump, a high temperature heat pump. Why we are doing that? Why we did that? First of all, we were looking at a product or a solution that could substitute the traditional gas boilers that, as we will see so far, at least in Italy, have the vast majority of the share of building heatings, at least in the residential segment. Of course, we were focusing on centralized heating with the idea to delete as much as possible the emission that heating is producing in urban areas. A third objective was the reduction of primary energy, particularly there where the gas boilers are used, to provide also a solution that could reduce the economic energy bill of consumers, and in summary, to change the mode in which heating is produced, not by virtue of burning something, but by virtue of electrifying a system that, as we saw also in the initial intervention, can enable participation also of customers to the balancing of the grid. Let's have a look to what have been the development of heating, at least in Italy. In 2020, as you can see, while in the production of electricity, almost 40% of the production is coming now from renewable sources, in the mobility system, a similar revolution has at least started up, although is a little bit lagging. When we look at the production of heating, the contribution of renewable energy in heating has been quite low in Italy. And if we look at what type of renewable sources are used, we can easily understand that the vast majority is renewable by regulation, but are heavily polluting. If we look at how the building heritage is done in Italy, almost 9 buildings out of 10 are heated with natural gas. A small portion with GPL, LPG. Some of them are still heated with gas oil, even in cities like Milan. If we look at the age of our buildings, 50% have been built almost 50 years ago and before. 1 out of 5 is considered to be in poor and mediocre states of conservation, and only few are in a very high energy class. And this, if you look at the terminal that have adopted in the Italian building on the lower right-hand side, 9 out of 10 buildings have radiators. And these radiators have been designed and above all sized in periods in which temperature was not an issue because they were heated by gas boilers. The result of that you can see in the evolution of the polluting contribution that the heating has had in the last 19 years, almost 20 years, compared to other sectors that produce pollution. And I've just taken as a reference the particulate matter 10. So while industry, road transports, agriculture, and other like waste have given their contribution to the reduction of PM10, the heating sector has consistently increased its contribution. Actually, it's the only one who has consistently reduced its contribution. The cone of light of how much heating is heavy in polluting our cities, our urban areas, has only recently come to the attention of our governments, at least here in Italy. My reading is that while innovation has taken off in several segments in other industries, in the heating sector, the innovation has not been applied so far. Not all buildings can have the privilege of having the whole distribution heating plant to be refurbished or heavily requalified. And therefore, what is the addressable market of most traditional heat pumps now is limited to the new buildings. Probably different from other northern countries in Europe, we do not have so much the habit of having heavy restructuring of the building, even deleting the old building and rebuilding a new building in the same area. We keep on having our national heritage as it is. What type of characteristic what type of characteristic did you want to put in our products? First of all, as I said, we want our products to be applied and applicable in buildings where traditional systems are there and they might not be replaced. So they have to work with cast iron radiators, typically put under small windows with a very limited exchange surface. We have selected for our heat pumps natural refrigerant. We didn't come to the heat pump producing heating coming from a chiller. We have selected several, about 125 at the time, different refrigerant, checking out which were the most efficient in producing heat, and not simply working, or sort of not simply looking at GWP, but also about condensation enthalpy at high temperature, critical point, etc. Temperature in the heat pump industry, when we talk about high temperature, there is quite an extended degree of discretionality. What is a high temperature? For us, a high temperature is 80 degrees. It's not 55 degrees or 60 degrees or less. And above all, a heat pump must be efficient at all conditions, not simply in all, not simply with low temperature of the plant, and where outside temperature is not too cold. And this is why, as a reference, we have privileged the recourse to low enthalpy geothermy in our applications. Here I show a simple, not particularly big application we did in a condominium that was built in the 70s. Is a condominium where we replaced a gas boiler with a heat pump working at high temperature. So the condominium has cast iron radiators. And in the last thermal season, we are now looking here what is the thermal energy that we provided, and which is the COP and the seasonal performance factor. This is a water-to-water heat pump. We have a first layer of groundwater at 12 degrees, and we return the water at 9 degrees, and we provide temperature to the system at 70, on average, 72 degrees. Of course, we have a climatic curve that fluctuates depending upon the external temperature. As we see, difficult is to assess what has been the economic savings made by the building, particularly in a period where gas prices and electricity prices have been changing so radically. We started from a period where the euro per standard cubic meter was 85 cents, and a kilowatt hour costed, the full cost, 23 cents per kilowatt, to a period nowadays where our gas, natural gas to residential business, is 1.76 euro per cubic meter, and the euro per kilowatt hour has become to 0.45. You can see what is the level of savings, other things the same, that has taken place. And you can also check what is the level of CO2 that we have taken out from this building. Where are our applications? Our applications tend to be in several segments, also in industrial context, in commercial context, in offices, and in the residential business. As I said, we have privileged addressing centralized systems. This from 115 kilowatt upside, but we also have developed some products for independent units of smaller size. And this is a little bit about it. Thank you for the attention.
Thanks a lot, Ferdinando, for your presentation. And I already saw that we have some questions from you, from Lorenzo. He is asking why did you choose to use geothermal sources, and why you chose natural refrigerants for the heat pumps?
Geothermal source. Geothermy for us is linked very strictly with our technology. The philosophy of using a heat pump for us is that it has to work efficiently when the heat is more needed. So for us, there is not the point of having a heat pump that when it goes around zero or below zero, the COP tends to follow, say, the Ohm law by using resistances or so. This is why we have, although we have also air to water heat pumps, but when it comes to deploy heat pumps in, say, climate that are colder, we can rely upon a natural source whose gradient is almost constant all year long. So regardless of the temperature outside, water in the first layer of groundwater is generally constant if we use an open loop around from at least in Italy from 12 to 15, 16 degrees in Milano, or to closed loop systems when we use geothermal probes. Of course, we talk about low enthalpy, and I guess that at least in Italy, I don't know, elsewhere in Europe, there is a good degree of confusion on what geothermy is. We are not talking about geysers here. We are not talking about producing electricity from very high temperature in the ground. We are talking about using a source whose temperature is lower than the plant that we aim at heating. And therefore, we have to extract heat and to raise it to the level that is required. And the geothermy allows to have more consistent and more efficient COPs and seasonal performance factor all year long, for the first part of the question. The second question, why did we use natural hydrocarbons refrigerant? Well, because they have a number of plus compared to the typically used F-gas. Earlier we talked about the GWP. The GWP of our heat pump is 3. No, it's not 500 or 600 or like the old F-gas. I remember the 134, 1300. So 1300 times more hazardous than CO2. Second point, because a critical point of our refrigerant is high, is 135 degrees centigrades, which means that we can reach high temperature. It's very hard to reach high temperatures starting from a level of natural source, which is relatively low, so having a jump of 70 degrees with a refrigerant whose critical point is not high. To give you an example, the 410, I don't know how much is still used, has a critical point of 71, 72. Third aspect of our refrigerant, at 80 degrees, we work with 1300 kilopascal. So we work about at the maximum temperature, we work at 13 atmospheres. Most of heat pumps circuits work at 35, 38 atmospheres. So this gives you an idea on how reliable or less reliable with the risk of losses you can have in the refrigeration circuits. And last but not least, we have a condensation enthalpy, which is twice as much several refrigerant at 80 degrees. That makes them very efficient when you have to deliver useful thermal energy in at high temperature. So maximizing the ratio between thermal energy and the absorption of electricity.
Sorry, I was muted. Thanks a lot for this presentation. You can maybe stop sharing, yes, and then we can see if there are further questions. I have one more question already, which is, I guess maybe particular to Hélène and Fernand, to you actually, on what is the market that you're currently active on and how do you plan to expand? This could maybe also be relevant to others. And then if there are no further questions, I may also want to ask you in light of the need to deploy sort of heat pumps and energy efficiency in the coming years, not only for climate reasons, but also to reduce our gas consumptions and in light of the high gas prices, possibly in the coming years to come still. What would be needed also from the policy side or in terms of finances or investments in order to make this happen? So what would you ask from policymakers or in terms of investments in order to realize this? So maybe I'll start with the question on the markets and how you plan to extend with Hélène.
Yes, today our first pilot sites have been in Sweden, and that's because the team developing the software are located in Sweden. But we now are also building a new site in Milan, actually, so in Italy, and we also have in the Netherlands, and we will now sign project in France and UK in the next coming months. So we see markets where we do have a strive to lower the carbon footprint, and the municipalities are many times the ones driving this, or local regulations, I might say. And what we do need is that we need, since our systems are not very big, but normally slightly bigger than one developer to make it worthwhile, because we want to connect different needs. We do think it would be very useful that these kind of systems are, we need some planning with us. We need some understanding how it works and what's being required to connect these different thermal needs to each other and the benefits of it. And some places they do have it and some do not yet have it, I would claim. So we need to have regulation with us and planning.
Thanks a lot. That's a very.
We also have it in Germany. I forgot.
I think that may have been clear, but thanks a lot for that clarification. And I think there's also some upcoming developments on also giving more resources at the local level to do this. Also,
yes, and it's a lot about this is really sector coupling at its core. How to make efficient thermal use of electricity and using it at the right moment, and also how that regulation come into play when it comes to the electricity market with the VPP and so on. We need to use electricity when it's available.
Okay, thanks a lot. Then I move to Ferdinando with the same questions.
Let me check if I remember all. Regarding the addressable market, we started 7 years ago. Our body center for today is Italy, mainly northern Italy, but now also in the southern part of Italy. Of course, in our plans, there is the possibility to go abroad. We have started having a few sales abroad, mainly in neighboring countries. So definitely our scope would be to expand where required, where needed, a product and a solution like ours. Regarding the reduction of primary energy, as I said, definitely it is not simply a matter of reducing emissions. It's also a matter of having at system level the possibility to be less dependent from primary energy. And we observe that particularly now in countries like Italy, but also in other countries in Europe, whereby the importance of being somehow independent has become urgent. And when things important becomes urgent, unfortunately, we have a problem in general. Regarding the regulation, I guess that that would be a very complex question to be answered. I guess that if all governments in the EU wants to put their money where the mouth is, they have to sort of have all technologies put in a merit curve and award those who better allow to achieve certain objectives, be them the reduction of primary energy, the less polluting energy emissions, etc. And one thing that we always have to remember is that the decision that we are taking today, we will bring them with us for the next 10, 15, 20 years, because we do not change a district heating or a centralized heating system every year. So if we now install, also by virtue of having incentivized some gas boilers or fossil fuel technology, there is no way that we are going to reduce and meet those targets that, at least in Italy, seems ambitious on one side, but on the other, not always in line with some, say, incentivation systems that have been deployed. So I really would recommend to be consistent, coherent, and independent in the thinking.
Thanks a lot. I think that's also a very good point indeed, to phase out subsidies for the things you don't want to have for the coming years, and also to make sure you reward those with the highest energy efficiency. I mean, we have eco-design, and I think this is on the table, so it's a good point. Then maybe also similar questions if you want to answer to Morten, and I'm not sure if Barry is still here. And there's also another question about, and Claudia's not here anymore, about hot water production by heat pumps and how that links to Legionella-free system. I'm not sure if there's any one of you who can answer that.
Yes, I can do it, because I tend to discuss Legionella problems every day at the moment due to this very question. And different countries have different regulations on this. And in some countries, the temperature demand is higher than others. And in some countries, it is worthwhile to have a look on going into a loop with the compressors maybe once every day, or sometimes twice a week, to kill potential bacteria off. And I think this is a very important question as well from a regulation point of view, because there are many countries where Absolutely. Legionella is not a struggle, and the demand of the temperature is much lower. Okay. So this could be adjusted. I think it's due to the old custom of having temperature for free, that it's still left in some regions.
Okay.
So we can lower it, and there is a system that works with the automatic cycles on this.
Okay, thanks a lot. Then I think good to see you back, Barry, as well. A question to you and to Morten. I don't know who wants to go first on what do you need from regulators to accelerate deployment, which is now urgently needed in the coming years?
If I can start. Industrial-wise, if you want to go low on GWP on refrigerants, you are faced with F-gas regulation phase down. That brings two things to refrigerants. One is flammability, the other one is toxicity. And if the politicians really want this phase down, we should actually also look at our EHS, our environmental regulations. You don't put a 5-ton ammonia system in the middle of a city without some sort of protection. But it's actually extremely easy to capture ammonia. On the other hand, very big HFO units like the one I showed you with 8 tons, it's a huge cost if that leaks and disappears. And it's flammable. So I have all what I need. What I also need is that our rules, codes, and standards for using flammable and toxic refrigerants are looked at holistic, because now there's actually a blocker for implementation. And we face it, we have to do it. We drive around each day with gasoline in our cars. When I was a small child, we actually had propane tanks. Also, you had cars running on gas. So we are looking at a parking lot in front of a supermarket with gas tanks in front of in a cage on each gas station. But we have problem putting 50 kilos of ammonia in a large warehouse or some. So that's really what I need. I need regulations that supports environmental friendly refrigerants. Okay, and if we don't have that, we are stuck longer with the others.
That's a very good point. Thanks a lot. And final word to you, Barry, for any.
Yeah, thank you. I think we need two really key things. One is European certification for real performance technologies. So right now we're stuck with the energy performance certificates. And in fact, we're requesting as part of your EPBD work that's going on at the moment in the European Parliament and the Council is to see whether we can both have a European certification for real performance technologies, so that we then give confidence to consumers that this technology is able to do what it says it can do. So that's one key thing. Then as we look at market design, is how do you reward that capacity? What kind of mechanisms can we develop so we can reward energy efficiency for the capacity it reduces in the system? And that is, I think right now, in terms of sort of making that possible in the real world is missing. And it's something we really need to look at. And I think this is something that the market design team of the European Commission needs to start looking at, is once we have certification of these technologies and therefore we can trust them, how do we then move to a position where we can actually reward that capacity through the market design? I think those are the two critical things that we need to see in the next months and years ahead to make this actually possible to roll this out and renovate buildings aggressively, to put them in place to make the heat pump rollout also successful.
Thanks a lot. Also very clear points. And just wanted to check, Davide, do you still want to say any final words?
Yes. Thanks, Femke. Just flagging that we didn't have the time to go in depth on this F-gas issue in this webinar, but we will certainly to in other webinars, the different opinions there, how to regulate this and how to best align this with the speed up of the market uptake for the different heat pumps. I think that today we managed to have a broad view of what technology is delivering. It can do, I mean, to deliver decarbonization of heating and cooling in different markets of the building sector. And I think also that I think we have the living proof that technology is there, solutions are there. It's just a matter to scale them up and adapt them in a very intelligent way to the existing building stock. Remarkably through Internet of Things and demand side control, but also integrating this new technology based on exchanging heat and cold, and also always having an eye on the fact that we have a time issue there, that we probably want to also change the old heating system, not necessarily always all of them after having the renovation, but maybe the renovation can come just right after. I mean, it's because for the sake of time, we have to roll out 10 million of heat pumps in 3 years, and it's a big challenge. So just also from the EB point of view, thanks a lot for all the panelists for being in the call, and thank you, Femke, for sharing.
Thanks a lot to you, Davide, and also to Antonio for the organization, and to all the presenters, as well as to Heike and Kieran Cuff for the video message. Thanks a lot, and to all the participants for joining us. And have a nice day.
Thank you. Goodbye, everyone.
Bye bye. Bye.